Melissa. Ask away, my dear. It sounded so serious. I have questions. Hi, Brandy. I'm serious. I'm actually wearing footy pajamas right now. Can I go over nomenclature? Sure. What do you want me to go over? Anything specific? Hi, Mackenzie. Want to just do some practice ones? We can do some practice ones. Does that sound like a fun idea? Do some nomenclature business? Let me increase the size of this. Hold on. Hey, Duncan. Well, Melissa, some of the old test had stuff on it that we didn't cover, like epoxides and ethers. What type of functional groups do you want me to go over naming? I guess would be a good place to start. Nomenclature are always good questions to ask because, I mean, if you can get it, and, you know, it's, the nomenclature part's easier than the rest of it, I think, for most people. So, I mean, they're almost like bonus points on the exam, so. Oh, carboxylate. Okay. So, okay. Yeah, we can do some of these. Let me know if you can see this okay, or if you cannot see it okay. It looks okay on my screen, so I think I can see the live chat box and the structures pretty well, so let me know if that's an issue for your screen and I can try and change it. Okay, so let's do, making me think. All right. Name that molecule. Hi, Lauren. My other class doesn't tell me that they're here, I don't think. They just stay quiet until somebody asks a question and then they pop in. So I'm going fix that. Okay. That stinks. One of my dogs made something stinky. It's gross. I don't like it. Okay. Lauren, Angela, and Lindsay. Hi, ladies. Okay, so those of you who are just joining us, we have been asked by Melissa if we could go over some nomenclature, carboxylate and carboxylic acid derivative type chemistry nomenclature. So this was the molecule I put on the screen. I think this is a good one just because it kind of highlights some of the, I guess, what am I trying to say? It's got a lot of the stuff in it that we've done before, but just incorporating this new subject. So, what is the functional group that has like the priority here? Now, I know we didn't talk about like priority rules of stuff, but alkenes and alkynes and alkyl groups aren't really on the priority list, right? So that means the only functional group we have to really contend with is the amide. Exactly. So that means the carbon that's in the amide should be carbon 1, correct? Yes. So if you looked at this and numbered that 1, 2, 3, and 4, you did a good job. Okay. So let's look at this and take it step by step. Come on, Twinkie. Sorry, he might bark, so if you hear a really loud dog bark, I apologize. Come on. He starts wanting on the bed, but he has trouble getting up, so he just roughs at me the whole time. All right, so number 1 has the amide. Well, we don't really have to put the numbering there. Hi! But I think it's good for us to remember that it's at carbon 1. Is there anything at carbon 2? Come on, Twinkie. Come on, Twinkie. You can do it. I have faith in your little legs. Come here. Twinkie's having some problems, kids. Give me a second. This will be kind of comical. Come on, Twinkie! Come on, Twinkie! Not you, right? Come on, Twinkie! Oh, I didn't know this. Okay, come on. Alright. Alright. Okay. Now we're cooking with fire. This is my life. That is my life. Okay. Oh no, am I cutting out again? Okay. So, where did I leave off? Let me pull up my paint again. Okay. So we have the amide at carbon 1, and then, good. It looked like it was fuzzy there for a second. At carbon 3, we have an alkene, right? So we should have something that looks like, whoops, that looks like that at some point, right? And then we also have, at carbon 3, a cyclohexyl group. Just like you would name, just how you would name a methyl group or an ethyl group or an isopropyl group. Guys, stop it. Stop it. Gross. I'm not even going to mention what they're doing. So let's put these pieces together. And we need to know the parent chain, right, which is butane. Technically butene. Stop sitting on my charger. Oh, for the love of God. These dogs are going to be the death of me. Okay. So the things that I need to put at the beginning would be the cyclohexyl. And I guess I should ask, is there any stereochemistry? The only place that we would really need to look at for any stereochemistry would be there we go, the alkene. But because this part here has 2 of the same groups on it, 2 hydrogens, it has no stereochemistry, right? So, getting back, we would basically end up having cyclohexyl, but-3-ene, right? But then when we put amine or amide or any of those things at the end, we take the E off and put amide. Make that so it's one word. So 3-cyclohexyl-but-3-enamide. That couldn't be any more awkward to say out loud, could it? But that's what it is. Okay, so if I... Whoa. Oh, I didn't know that was a thing. I guess I'll just cover that up. Okay, so let's do another one. Let me go back to KimSketch because it's easier to draw them in that. Let's do another one. because it's not made out of a benzene ring, it's a cyclohexene. So the benzene has to have the 3 double bonds in it. I mean, we can do one. Let's do something long. Okay. And yeah. And we can put a phenyl on it. We can do that. Not a problem. Right there. Okay. Now we got a phenyl. So let's try and name this one. Now this one's a carboxylic acid, but what I'm going to do is I'm going to change the functional group at the end from a carboxylic acid to some of the derivatives so we can kind of see how the naming changes. Stop sitting on my computer cord. All right. So can I get a parent chain? Oh no. Interesting. Okay. Well, it said you might experience some buffering because it's got low video output. I don't know. Okay. So we've got an octene, an octane, and a nonane, all from Melissa. So I guess I better answer because otherwise she'll just keep coming up with. I think we have Comcast. Isn't that what we have here in Clarksville? I don't think we have Charter in Clarksville, do we? Oh. Then that's probably it. Because I have the same cable that's in Clarksville. Okay. Let me copy and paste. Make it giganto so we can see it. And let me switch my screen over. Okay, so I am in agreement with, let's see, Melissa's third go around with the naming. It should be a no name. 1, 2, 3, 4, 5, 6, 7, 8. So that makes that one down there 9, right? So longest continuous chain that has our priority functional group on it. And in this case, that's a carboxylic acid. So if we put in kind of the parts that we, the parts that are important, we have that oic acid thing that we're going to have to stick at the end. I'll go ahead and put nonane on here. What else do I have? At carbon 4, I have a hydroxyl group, and at carbon 8, that's when I have a phenyl, because if you notice, it's got the benzene ring with the 3 double bonds inside. So if we put that together, we would end up with, let's see, so the hydroxyl would come before phenyl, because H becomes before P. So 4 hydroxyl, 8 phenyl, nonanoic acid. I always thought nonanoic acid sounds fun. Okay, so if you got something that looks something like that, oh, yeah, no, that's everything. Did I get everything? I think I got everything. Now we do have 2 chiral carbons on here, carbon 4 and carbon 8. I did not indicate any specific stereochemistry there, so you wouldn't be able to name any stereochemistry. But in theory, you know, I could have asked some stereochemistry on that, and you'd have to come up with either R or S. Because there's 2 stereocenters, you could end up with a total of 4 possibilities, the SS, the RR, the SR, and the RS. So just kind of remember the stereochemistry and how that applies to these things. Now if I go back to ChemSketch, let's see what would happen if we do some modifications to this molecule. Okay. So in this case, we have the negative charge on the carboxylic acid, so it's no longer called a carboxylic acid, it is a carboxylate anion. Okay, so in this case, you guys are being weird. My dogs are being really special right now. Actually, you know what? I can just... Twinkie, nobody wants to hear you doing that. I'm so sorry. This is why I go in my closet sometimes. Okay. Dog grunting aside. Sorry about that. In the example of where you have the carboxylate, you just name it as O8 at the end. That should be very similar to, so like the one that you know common name for from general chemistry is acetic acid and acetate. So it has that ATE ending for the deprotonated form of the carboxylic acid. The only difference is that in like the IUPAC terminology, we put that O in there before the 8. So that's how you would name that. And if we wanted to put on, let's see, let's put on a propyl group, okay? If we wanted to name that, it should be the exact same name, except now it's going to have a propyl in front of it because we've put a propane attached to the oxygen. Okay, so there we go. So check this out. If you have one of these, the interesting thing is that you don't get the let's see if I can do a drawing on this. But there was a little sketch thing. I might be wrong. Oh, well, it doesn't matter. But basically that propyl in the 4 doesn't get a hyphen between it. Do you guys notice that? It's a little different. Usually we see some sort of hyphen between a number and a letter. In the case of esters, you put that like in the very front of the name, and then you put the rest of the name after it, and there's no hyphen in between. The only thing that you would put in front of that name would be stereochemistry. So if I had specified, and I guess I can do that. Let's specify the stereochemistry here. So it should be able to come up with that. Oh, actually I lied. Okay, so they put it in the between the propyl and the hydroxy. Don't worry, I didn't put that on the exam. But yeah, that whatever is attached to the oxygen gets put at the very, very front. Apparently, of even the stereochemistry, I didn't know that. Oh, hi, Melissa. Do I know when it's hydroxy versus hydroxyl? So you call it a hydroxyl group, but in the naming, it's always hydroxy. So there's no name that you're going to give something that is going to be hydroxyl something something. It'll always be hydroxy. I don't know why there's a difference in the naming for that, but there is. So I don't know why it's called a hydroxyl group, but we name it as hydroxy. But I can't think of any exceptions to that. I think that's the case 100% of the time. Okay. Now let me give us one that isn't... Earlier it was hydroxyl. Oh, that's because I messed up. I'm sorry. I'm looking back at the screen now. Yep. Fix that. If you guys are writing down notes, which I know sometimes you do, fix that. Won't let me click on it. I can't edit it. Why can't I edit it? Okay, fix it. But yeah, hydroxy. And then let me do one more of these. Did my camera just freeze up? What the heck just happened to my camera? Can you guys hear me? Oh, son of a biscuit. Come on. Really? Here we go. Mine was all frozen up. I don't know if yours froze up. I think I'm just paranoid. After last time, I'm paranoid of that happening. Okay, so let's do another couple of examples, and then we can get off of the nomenclature if you want and into something else. So I wanted us to do... I'm going to have to fix that. I was just trying to make a dinging. I was trying to do an anhydride. Actually, Duncan. But I failed miserably at my structure. I don't know if you guys know you can do this in ChemSketch. If you go under Tools, the second one down is Clean Structure, and it'll make it pretty for you. So this is a different anhydride. That's not propanoic anhydride, but it is an anhydride nonetheless. So we can do that one, and then I can do the propanoic anhydride too here in a second. So on this one, you basically, and I think I'm going to do this one in the paint program. That is butanoic anhydride, Duncan. Very good. So for those of you who are having trouble seeing the anhydrides, flip this back over. I think it's taken me a good 2 years, but I'm finally getting the hang of flipping back and forth between the screens so frequently. Okay, so what I want you to look at, let me grab a color here. I want you to think of this as a carboxylic acid, right? If that oxygen has a hydrogen on it, which it doesn't, but let's act like it did, how would I name it? I would call that butanoic acid, right? Because I have 1, 2, 3, 4 carbons in the chain. Okay. Now this is a symmetric anhydride, which is the only thing I said I would make you guys name. I'm not going to give you anything that's an asymmetric anhydride because you'll probably never use them, you'll probably never see them, and there'd be no point. But if you have an anhydride that's generally symmetric, is how you make them, and you would call that butanoic acid, so then the name of the product is just butanoic anhydride. Instead of acid, you just get the word anhydride on there. Duncan, did I just answer your question about the different names? I'll show you. Here, look. So if I have this one, tools, generate, name for structure. Okay, so there's butanoic anhydride. Now let's say I have another group there. So now it's asymmetric, right? It's no longer a symmetric anhydride. So I can generate name for structure. And so now you're going to see it's a lot more complicated. But instead, it's just called butanoic pentanoic anhydride. So it's kind of like an ether where you name whatever's on each side of the oxygen. In this case, you still do, but it's an anhydride instead of ether. And then it still gets the alphabetization rule, so that's why they put the butanoic before the pentanoic. But I'm not going to ask you that. That's just an FYI. If you're interested in knowing that information, that's fine. Okay, ask me something that's not naming. Then we can get back to naming if there's more questions. The problem with your touch screen is if it's dirty and you try and wipe your screen, things start moving around. It's this Twinkie's tail. He's got the tail of a fox. It literally drags on the ground when he walks because his legs are so short and his tail is so long. An imine reaction. Okay, what do you want to know about it? You want to just do an example? So, Melissa, quickly, it's technically the carbanion. If it was the enolate, you'd be making a bond with the oxygen in the new carbon rather than 2 carbons bonding a new bond. I've been showing it to you going from the carbanion to the enolate, so that way you can see the 2 resonance structures that stabilize it and then continue on the mechanism with the other one. And we can do an example of that too if you want. Brandy, I have no idea what that crying face means. Are you sad? Are you happy? Are you dying? I really don't know what that emoji is. People use it all the time and I feel so stupid because I have no idea what that's supposed to be. Okay, I'm going to go away for a second so you won't be able to see me. But I'm going to make my screen for this bigger because those are really big reactions. Ow! Why are you walking on me? I promise I'm still here, yelling at my dogs. Okay. I'm basically a crazy cat lady, but I don't like cats, so I have crazy dogs instead. Alright, and let me grab a brush or a pen, and then, you know what? I did this the other day in the other class. I'm going to do it now. Let's be festive. So let's do an imine reaction. Let's do one where Me is shorthand for methyl, if you remember. So this is just cyclohexyl methyl ketone, I believe is the common name for this. And then, yeah, let me put on aniline. Trying to make those as lone pair. Okay. So the first things first, we use a little bit of acid in this to basically get it started. That's what catalysts are, right? They're things that help things get started. And so in this case, the first thing that happens, and please look at this and in your mind say, carbonyl plus amine plus acid equals imine, okay? If you can remember that, like, this is like baking a cake, and those are the ingredients that will give you an imine, then that'll make things easier for you. And I can write that down if you're like, what did she just say? An aldehyde or a ketone plus a primary amine, or you can use ammonia, plus some sort of acid catalyst is going to give you an imine. Okay? That's the only set of reaction conditions that we've seen that will give you an imine, and we haven't seen those set of reaction conditions do anything else. So, right, you can pick out things based off that. If you have trouble recognizing these reactions, remember that those are the things that you need to react, okay? So the first things first, I'm going to protonate. I'm going to show these as reversible arrows, and I'm going to try and show it as small as possible because, oh shoot, because otherwise I'm going to run out of room really fast. Okay. So there we have our protonated oxygen from the carbonyl. And then that's when our nitrogen can attack. And it's going to attack the carbonyl carbon, because remember the carbonyl carbon has a partial positive charge on it. And I don't think my finger is sufficiently small enough to write one that tiny. Maybe if I use this. That looks so bad. I'm sorry. Here, if I use the mouse, it's a little bit better. But that's the partial positive charge. And when that happens, those electrons can swing up. You can't not swing up those electrons, right? Because otherwise you'd end up with 5 bonds on that carbon, and we all know that's a big no-no and can't happen. Oh, criminy. I can't keep track of my color coding. And I just started. It's pretty bad. And then got my nitrogens. I'm just going to use my shorthand for benzene there and put my positive charge on my nitrogen. Okay? So now the next step is just those series of protonations and deprotonations. And one of my students in the brief organic class this week, because we also covered this material this week, their lessons have been coinciding with yours for the past about week and a half. But they were actually counting the number of steps. And actually, and I'd never looked at it this way, but somebody saw a trend that the number of steps, I think, and the arrows and everything were exactly the same between imine chemistry and acetal chemistry. So that's just maybe a little something you might want to look at into how that works, if that might help you out. Now, if I have acid, I have its conjugate base laying around somewhere, and I'm going to use that to deprotonate that amine. So now we have this situation. Nothing's charged, but something needs to be. Okay? The oxygen is going to be able to pick up another proton. That's why we do this in weak acid as our solvent, or not weak acid, but a dilute acid. I misspoke. That's one of my most common mistakes, and it's one that drives me the most bonkers too when other people do it. Oops. Okay, so generally speaking now, there's a couple different ways that this gets shown. I don't actually remember how I did it in your all's class. One thing that can happen is people will usually draw, and I think I did it this way, where these electrons came in and the water left. I'm pretty sure that's the way I showed it, because that's how I usually show it in my other class too. But another way is that some people will show the water leaving and then the nitrogen kind of swinging in, or it getting deprotonated and those electrons caving in. I think they show it that way because in biology it happens that way, but as I've mentioned, we don't tend to show things the same way in here that you do in biology. Okay, and then the very last step on that would be a deprotonation. And I've basically completely run out of room. Hopefully this is fitting. Let me double check. So I can't see what you guys are seeing right now. Hopefully this looks like something that you can understand. I don't have the text box up, so this is, oh sorry, I just pulled up the box. Justin says this is Heath. The mechanisms in the book for imine have the primary amine attack the aldehyde or ketone first before it's hydrated. So that's it. Do you remember in class? Hopefully you remember in class. If you were there that day, I mentioned that there's a lot of different ways that you can draw the mechanisms for these, and pretty much all of them are right. As long as you have all the protonations and the deprotonations, and you don't have anything as a leaving group that you know can't be a leaving group, like OH minus, you'll be in fine shape. And if you look at like 10 different internet resources, you'll probably come up with at least like 5 different mechanisms that they're using. It's just the nature of imine chemistry and acetal chemistry that's, I've seen a lot of, I don't want to say conflicting, but I mean they're not the same, so I guess in that case they are conflicting. But hopefully that this mechanism made sense. Let me go back. So yeah, I know what you're saying, Heath, and that's perfectly fine too. I always accept reasonable imine and acetal reaction mechanisms because there are so many reputable ones. The truth is we don't always know the order of what gets protonated. On the 5th step, the nitrogen will have a hydrogen on it. 1, 2, 3, 4, 5. It does have a hydrogen on it. It's just ugly. Here, look. Sorry. I ran out of room. That goes to that structure. And then this came down here. So this is the hydrogen on it. I just ran out of room because I have a limited size screen. I'm sorry, guys. I was hoping that wouldn't be confusing, but I guessed wrong. And then, let me scroll back up here real quick. Melissa wanted to know on aldol reactions, is it the enolate or carbanion that reacts with the aldehyde? So let me just quickly show one of those. I want you to be able to look at a lactone or a lactam and say, yep, that's a lactone or that's a lactam, but we're not going to name any of them, Melissa. That's just a functional group I think it's useful to recognize. For those of you who don't know what she's talking about, lactones are the cyclic esters, and lactams are cyclic amides. So if they're in a ring and it's an ester or an amide, then that's a lactone or a lactam, respectively. Did you guys want to do an acetal reaction? Wasn't that what you asked for? Oh, that was an aldol reaction. Do you want to do an aldol reaction or an acetal reaction? I guess we can do one of each. I'm just waiting for feedback. Aldol, Vidig. Okay. We can do both of those. Oh, shoot. Did I just pull up the wrong screen? I did. Hold on. Here we go. Okay. So an aldol reaction. So aldol, aldehyde, becomes an alcohol, but then it dehydrates, right? And it reacts with a ketone to form a carbon-carbon bond utilizing enolate chemistry. So let me write that down. Aldehyde plus ketone. And then we have to use some base. We usually use OH minus in there. Equals aldol equals dehydrated aldol, which is an unsaturated carbonyl, okay, beta unsaturated carbonyl. So those are the recipe conditions. As I said, it's kind of like how many eggs do you need to make a cake and how many pounds of butter. Acetone is a good example of a ketone for this. We already used that one in lab, so I'd like to give us another example that's not one that we've seen in lecture and in lab. Hopefully I can come up with something. So, let's do an aldehyde. Okay, so this would be 2-methyl-propanol. This could also be, let's see, which one would that be? Isobutanol, right? And then I need a ketone, so that's our aldehyde component. For a ketone, I like to give you guys examples where the ketone only has one set of alpha hydrogens. I do that because otherwise you get quite a large mixture of products, and I think that that would be difficult and or confusing. And I kind of think that this reaction is kind of hard to visualize as it is without doing that. Okay. So these here are the makings for an aldol reaction. So I'm going to deprotonate. These electrons will come in and form the carbanion. Now this one I'm showing as one direction reactions. Okay, so I'm going to abbreviate my phenyl ring again, my benzene ring. And then on my carbon here, I'm going to have that. Okay. There's a resonance structure that stabilizes this mess. We've talked about that a little bit. And that is the enolate structure. Okay. I'll be honest, I don't remember if I talked about this with your class or with my other class. I think it was with both of you that I talked about how this structure here would be the more stable of the two resonant forms because it puts the negative charge on an electronegative atom. So Melissa, earlier when you were asking when it does the chemistry, if it's working through one or the other, okay, you need to realize that resonance structures exist as a hybrid of both, right? The pictures that we draw aren't really super representative of what they actually look like because they're actually a hybrid of both. But what we know is that the carbon is what ends up forming the bond, not the oxygen. And so the way that we justify that and show that using our arrows is to push this in here, come out, oh, I'm going all the way over, and attack the partial positive carbon on that, okay? So now I've got, and I like to keep it consistent if I can. I think it makes it easier to see if you basically draw these, oh, wait a second. Like just trying to erase that bond. I thought that would be easier than it is. Okay. Oh, come on. I'm sorry, you guys have to hear me talk to my computer all the time. Like, come on, don't be that way. Okay. And so now I'm just going to show that connecting to certain carbon groups, right? So this is the carbon. It's the one right there that I'm highlighting in red that forms the new bond with the other carbon, right? It is connected to that carbon right there. So, okay, what is that carbon connected to? A phenyl, and it's got a double bond to an oxygen, right? So in that case, that would be kind of the first of the products. We would want to protonate that, right? And so, and I'm not going to color code this. But so here is the beta hydroxycarbonyl, right? So remember, here's the alpha carbon. So that's the beta carbon. It's got a hydroxy on it, and at the carbon 1 position there, we've got the carbonyl. So a beta hydroxycarbonyl. Okay. Now we know that those spontaneously dehydrate, so I'm going to have to scoot that down a little bit, sorry. And what I've just been showing in class, and I'm okay with you guys doing it this way also, is just to show water leaving. Okay, I'm going to make the assumption, and I know in some of your all's cases it's wrong because you have not successfully shown this, but I'm going to make the assumption you guys know how to do a dehydration reaction. And if I asked you for a dehydration reaction, I want you to be able to show it. But for an aldol reaction, the mechanism is long enough as it is that I don't think we need to show both in one system. Okay, so we're just going to make this shortcut. So what you need to remember is that the whole point of this is to form conjugated double bonds between the carbonyl and the two carbons. So the hydrogens that have to get deprotonated are the ones that are here at the alpha position, okay, as well as that OH. And so when you do that, we're going to get that, and that is our product. Now, if we wanted to go through and name that, we could. That would be a hard name. Let's see, 1, 2, 3, 4, 5. So we would name that, I believe, as a pentane. Technically a pentanone. We have an alkene at carbon 2, so it would be actually 2-ene, 1-one. And then I have a 1-phenyl, 1, 2, 3, 4 methyl, pent 2-ene, 1-one. And then actually at carbon 2, I have some stereochemistry to tackle, and that would be E stereochemistry. So there we go. Okay, I'm going to switch back now so I can see the text box. So Duncan, if you show the mechanism as I just did it, I'm giving y'all full credit. This is the same way that we did it in class. I'm fine with it that way. So if you want to show the dehydration component of that, where if you wanted to do it kind of shorthand, you can, and I'll show you how. You can take base, and you basically do something like this. This is how a biochemist would show it, and it's also how most organic chemists would show it. This is obviously a little bit different than how we've done them in the past because I've always shown it being protonated before. But in this case, we're going to show it more like it's a concerted reaction when we know it's actually not. And that's just for the sake of brevity, to make it not as long, okay? So if you want to show something like that, I obviously don't count off for it. It's not part of my grade. Twinkie, what are you doing? He's rubbing his butt on me. He's being weird. This dog is special. Okay. I'm back. Well, I mark you off if you show the enolate bonding with the aldehyde. Well, yeah, because the enolate doesn't bond with the aldehyde. So just to be clear, to make sure I know what you're talking about, the enolate bonding with the aldehyde would look make sure you guys have the same screen I do. Okay. So an enolate bonding with an aldehyde would be this, and you would get a very different product, right? Your oxygen would be like that, right? I'm sorry. So I'm hoping you guys notice that that is incorrect. That's different than what I showed you. Okay? And then let's see. Oh. I had the double bond on the CH2 bonding with the other carbon, which can't happen since we're forming carbon-carbon bonds. Duncan, I don't know what you're asking me. The carbon-carbon double bond is exactly what we have here that reacts. It's this one here. That's the one that's going to go out and attack your carbonyl. Twinkie, you're very passionate tonight, and I get that, but you've got to stop. That's really grossing me out, man. I'm not sure I know exactly what you guys are talking about. Okay. Yeah, send me an email what you're looking at, because, I mean, you're supposed to be showing it from the carbon-carbon double bond. You can't show it from the oxygen. This is the enolate structure. So it's the enolate that's doing the chemistry. So Melissa also asked for a Wittig reaction. Okay, so remember that a Wittig reaction kind of contains two different steps. Fix that, sorry. It contains the formation of the ylid, and then it has the actual Wittig reaction itself. Yes, I'm wearing soft monkey pajamas. So let me think of one. Actually, so let me pull this up in Kim Sketch. That might be easier for this. So if you remember, we have to start off doing this with triphenylphosphine. I think it'll make me put carbons on there first. Okay. Now, we did kind of show a shorthand for writing this that I'm perfectly okay with you guys using. I don't think Kim Sketch has the ability to draw the shorthand with the little circle with the line through it, but if you want to do that, you can. It's kind of just an easier shortcut to drawing benzene rings. So the triphenylphosphine, if you recall, is kind of like nitrogen, right? And it's going to do things similar to nitrogen. One thing that it's going to do is to be able to attack any kind of alkyl halide. Okay, so I'll do this one here with bromine. Okay. So you end up with this weird rude tonight. I didn't get home till really late, which is why they're kind of acting crazy. I just got home at like 7:30, so sorry for all the dog in this video. Twinkie's being very R-rated tonight. I don't... Just a second. Hey Brandon, can you come and get one of the animals, please? I'm having some difficulty doing a video because they keep wrestling on the bed. Twinkie made Red his girlfriend tonight. It was a little weird. Okay. He's being so stupid and cute. I don't know, can you like offer him food or something?
Come on, Red.
Go get him, Red. Don't jump on Onyx. Okay, just close the door. I'm going to be with you guys at least another 10 or 15 minutes. It's been taking so long to get through just because of him. Those two wrestling on the bed. Okay. Where was I leaving off? This way. Open it up. Make sure you guys are seeing what I'm seeing. Okay. Oh shoot. It disappeared on me. Just trying to make it bigger. Okay, there we go. Okay, so remember that phosphorus does some kind of unusual chemistry. It's going to look a lot like what you see with nitrogen, except it does this whole Vitter-ion business that we don't normally see with things like nitrogen. So I'm going to show that. And so what you end up with is something that essentially yeah. Okay. And this kind of exists in resonance forms between the phosphorus with 5 bonds and the carbon with 4, back and forth. But what's important is that you just kind of look at it and use it as a carbanion. So if I want to put in some sort of carbonyl, and I'll just be easy on this, let's just use acetone. Easy meaning it's easier to draw. Okay. You basically get this weird intermediate where oh goodness gracious. I think I'm getting tired, guys. My handwriting's even worse than normal. Something I'm doing is looking very wrong here. I don't like the way this looks. I'm not doing this right. See if I can find a better example. Give me more info in my brain. I remember having this issue in class. I don't know why. I guess I just always feel like it doesn't look right. But, I mean, I should just give you guys the example that I did in my research lab. Because we literally did this reaction this semester. Oh, that's what I did. I keep forgetting to deprotonate the carbon. My charges don't work. Okay, let me try that again. I know you guys are probably like rolling your eyes at me right now. A little embarrassed. Okay. This is one of those things, I know you guys have probably had this experience if you have any level of test anxiety. It's funny because you'll be doing okay, but if you do bad on anything, you automatically will keep doing bad, it seems, because you've like lost the confidence that you can do it right. I think this has happened with me in the Wittig reaction. Even though, as I said, I literally did it in my class, or in my lab this semester. It's on the poster we're presenting tomorrow. We did the Wittig reaction. Okay. Now, this is the one that kind of exists in equilibrium with another resonance form. Okay. And let's see. Because that carbon has a lone pair of electrons on it. Okay. So real quick, I'm going to scoot back to the chat box, just make sure you guys are still with me. Okay. Now this is where you have the carbonyl reacting with a ketone. Or rather, the carbonyl reacting with a ketone, listen to me. I need to sleep. This is where you have the yelid, the Zwitter ion, reacting with the ketone. This also works for aldehydes. Okay. Now some people show this as a concerted mechanism. I tend not to do that. And I think that's because it is actually a stepwise reaction, but a lot of people show it that way. So if you see something online where it's like they're doing the steps, but they're doing them all at the same time, please do not do it that way. I dislike that immensely. Now remember that phosphorus, even though it has an octet on it right now, it's still going to have a positive charge because, if you remember, phosphorus has a valence of 5. It's the same as nitrogen. It's just, it can expand its octet because it has d orbital electrons in the third shell. So now you get, I'm going to put this in another color so it's a little easier to see. Here. Here. In there. So some people show them this way. That's what I was saying. If you show it concerted, that's how they're going to show it, like everything happening at the same time. That's the one that I dislike. So instead, just be careful. I guess I can draw these as skeletal structures, can't I? And then when you go in to basically do the chemistry here, you get that. And then the product of every Wittig reaction is triphenylphosphine oxide. You have to purify it. You usually have to use column chromatography for this. So that's the Wittig reaction in all of its glory. Melissa, you just said you wanted to see an example of it. I don't know if that's all you needed, if that was sufficient. Let me know in the chat box. There's a resonance arrow right here, because those are resonance forms. If you want to, you can put this kind of thing in brackets if you like. A lot of people do that when they're showing the different resonance forms that contribute to something. Okay, and I'm going to check my email because Duncan said he sent me an email. Duncan, that's exactly what we just did, sweetie. That's exactly the same mechanism that we just did. I'm not sure I understand what the question was. The enolate is the one that swoops in and attacks. Melissa, that was far from perfect. I had to do it twice. I keep forgetting to deprotonate the carbon. Don't forget to deprotonate the carbon. Don't pull a Dr. Mann. Oh, and Duncan and Melissa, you guys both had questions on the enolate. Maybe it's because on the board I literally named it enolate. I didn't do that on this, so maybe it was confusing. That's a possibility. Like making goofy faces at you guys. I feel like you guys are drying up on me here. Maybe you're as sleepy as I am. It was kind of a long day. Long day for me, long day for you. It's usually how it is at the end of the semester, isn't it? Melissa, that's exactly what we just did. That's what happens. If you have an enolate, right? And here's a carbonyl, right? This comes in, and then the double bond of the alkene is what attacks. So that's what we keep doing. And that is what's in your notes, because Duncan just sent it to me. So I'm not sure what the confusion is on it. Okay. Duncan wants to know if we can do an acetal reaction mechanism. We can. And with that, I think we'll be done, because it's already 9:15. Okay. Is Brandy still here? Brandy, are you there? You're not talking. You always chat. What would the double bond attack rather than the negatively charged oxygen? Melissa, this is exactly the same question you asked me earlier. The answer is because it doesn't, right? It's always an issue of thermodynamic stability. So it doesn't attack because it doesn't. The product that it forms is more stable doing it that way. Carbons make stronger bonds. Carbon-carbon bonds are stronger than carbon-oxygen bonds. Okay. Yes, Brandy, you're a very good listener, and I appreciate that about you immensely. Okay, so let's see. Duncan wanted to do carbanion. Right, but it's the same thing. So those electrons are the same electrons regardless of whether they're on the carbanion or in a pi bond on the alkene. So you can show it either way, but they're still the same electrons regardless. All right. So grab some colors. I do not like yellow. Did the light bulb just tickle? Did it go? Oh, there it is. There we go. Oh, you know what? I'm going to go back to the big one because this is so big. Sorry. Sorry, guys. I don't know. I think I had it over here. 3, 4, 5, 6. 3 pentanone, or hexanthurion. And we'll use isopropanol. That'll work. Okay. Oh, look at that. I picked Halloween colors. Well, that's fun. That was unintentional, but I like it. Okay. So that is the first exact step that we did for the imine chemistry, where we protonate the carbonyl. The second step is exactly the same thing as we do with the imine chemistry, except in the case of an acetal, you use an alcohol rather than an amine. Okay, so same exact reaction. Now we have an alcohol. I'll just deprotonate that real quick. So, still, same chemistry. We haven't done anything different yet. Then I get another protonation because remember, we're doing this in acid. That successfully makes water, which we all know is a good leaving group, right? And in this case, this is where it's different. So I'm going to literally outline this in yellow. This to here is all exactly the same as what we did on imine chemistry. So 1, 2, 3, 4, 5, 6. Literally the first 6 arrows are exactly the same, with the exception of this oxygen is a nitrogen in the case of imine chemistry. Now in imine chemistry, because the bond down here, I don't know if you guys can see me highlighting that, is a nitrogen, and nitrogen can get 3 bonds, it just folds those electrons in and kicks off water. In the case of acetal chemistry, that is not what we get because we're working with oxygen instead of nitrogen. So it is another molecule of the alcohol that comes in, kicks off water. And then you basically would have this, right? And then the last step is the same, where we have to deprotonate it. Let's see if I can scoop that down. Okay. So hopefully that makes sense. Oh, shoot. So that's a fun looking weird little structure for our product, but that's what we would get. I hope that makes sense. I can shrink this a little bit so you guys can see the whole screen. Hopefully that's not too tiny to see. Pull my chat box back up. You guys got silent on me again. Okay. So what, Duncan? Say starting material for the alcohol has one of the end and the beginning. Has one what? A ring. So you're talking about a dial? You can use a dial to get a ring. Who's on first base? You guys make me stupid laugh. I love you. Yeah. So for anybody that's wondering what Duncan is talking about, let me show you, because that's a good question. So something that I mentioned very briefly yesterday, and I'm not going, there's no test question on this or anything, but I mentioned something called protecting groups, where like if you have something that might do chemistry and you don't want it to do chemistry, sometimes you have to change the functional group to something that you can easily turn back. One of the ones that gets used a lot is a functional group or a group protector for an aldehyde or a ketone. Now, because imine chemistry is reversible, you in theory could use that as a protecting group. You can also use acetals, which are also highly reversible. You're aware of this, right? So let's say you are using this molecule here, okay? Oops. So this is ethylene glycol, is the common name for that, okay? When you go in to put those alcohols on the carbon here, do you remember how I say intramolecular reactions are faster than intermolecular reactions? So what you end up getting as a product there is something that's going to look kind of funky. So, but this is a good question because there's a lot of problems in the book that look like this, because this is a really common technique for protecting alcohol or aldehydes and ketones. So you would end up with that product. Duncan, is that what you were talking about? Let me make that pretty. Tools, clean structure. There we go. Oh, look at that. That's so much better looking than what I had. But because that's reversible, all we have to do is add a little bit of acid and a little bit of water to shoot it back the other way that it came from. I'm sorry, my mirror or my camera's mirrored, so that way. I'm pointing to my right, but it's showing me pointing to the left. That's very confusing, I guess is the best word for it. But there's different functional groups like that, right? So if you have that type of functional group, though, right, with the ethylene glycol protected group, that's not going to do aldehyde ketone chemistry. It's not going to react with lithium aluminum hydride. It's not going to react with sodium borohydride. It's not going to react with Grignard reagents. It's not going to react with anything that's normally going to attack a carbonyl. So, right, let's say you wanted to, you know, make something, right? And I think that this is a good, if you guys want to humor me for like 3 minutes, this is a good example. Oh, shoot. What did I just do? Where'd my screen go? Is that better? So let's show you something. So let's say I want to make trying to make this work to give you guys an example. Okay, so let's say I'm trying to make something like this molecule I have on the screen from benzene. Okay, we know that this here is an imine, right? We can't put an imine directly on the benzene ring. We have to do Friedel-Crafts acylation reactions for both of those, right? Well, okay. What you can do is put one of these on here, put a protecting group on it, put the other one on, then make the imine, then take the other protecting group off so that you are left with this. Okay, so that's how protecting groups work. You basically put them on to keep something from reacting, and then you pull them back off again. And some protecting groups are really easy to come off. Amines and acetals are very easy, as shown in class, right? I keep showing them with reversible equilibrium arrows for a reason. There are protecting groups that get really funky names like MOM, methyl methoxy chloride is a good protecting group. There's a lot of them out there for different functional groups. And so if you were in a situation where you were trying to do a synthesis and you were like, I need a protecting group for this, you might have some in your mind that you already know of and want to use. If we'd have had like 2 more weeks in the semester, which we don't, I would have covered protecting groups and chelating agents, but we run out of time. That's how things are. But anyway, you guys were kind of trickling down the questions anyway. I'm going to go to bed early tonight because I'm really tired, and tomorrow I have the symposium. So I think that if you have any last minute questions, if you can get them to me before 11 o'clock, I'm going to try to go to bed before 2 a.m. because I'm really sleepy. And if you have any questions, you guys can ask me. I already have the exam printed and in my box, so tomorrow all I have to do is walk in and hand them out to you guys. But the parking might be bad tomorrow. It was bad yesterday, and I think it was bad today, so just kind of plan for that ahead of time. I always try and give you guys like as much possible time until they kick us out of the room. I'll go back to the beginning of the video where I said go get some hot chocolate and footy pajamas. It's cold out. Everyone needs footy pajamas. So I guess that's it. I'll see everybody tomorrow. Hearts. Sorry my dogs were being such a pain tonight. That's why this video went so long, is I was having to deal with them. So such is the way of working from home, I guess. Good night. I will see everyone in the morning. You can totes bring in pajamas tomorrow. I will not judge. You guys will love this. Seriously. Footy pajamas. These are great. Look, they have little sock monkeys on the feet. Isn't that great? like a child. All right. Good night, people. I'll see you tomorrow.